Good morning. Section 2.1, we're going to talk about the definition of derivative again today. But today I want to focus in on an alternative form of the derivative, also estimating the derivative numerically, and the special tangent problem. You're going to love this special tangent problem. So alternative form. We can use the alternative form to find the value of the derivative at a given point. But we have to be given that x value in order to be able to use this form. This form is going to give us f prime of c, where c is a constant, some number, is going to equal the limit as x goes to that constant of f of x minus f of c over x minus c. That should look very familiar to us because it is very close to the definition of derivative. Remember, the definition of derivative is the limit. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So notice very similar in those forms. But now we're going to a constant instead of taking h going to 0. So can we find f prime of 2 if I give you the function f of x equals x times x minus 1? Hopefully, putting into this formula, we can. So we know that f prime of 2, they're telling us that c equals 2. So our limit is going to be going to 2 as x goes to 2 of f of x. Well, we know f of x is x times x minus 1. From that, we're going to subtract our f of c. Again, c was 2, so if I plug in 2, I get 2 times the quantity of 2 minus 1. 2 times 1 gives us 2. And from that, we're going to divide x minus c, or x minus 2. We can go ahead and clean this up. We have x distributed through, so we get x squared minus x minus 2. If I were to plug 2 in, we're going to end up with 0 on the top, 0 on the bottom. So it's going to be indeterminate form. So we're going to have to do something with it. What we can do is factor that top part. So we're going to look at the limit as x approaches 2 of x minus 2 times x plus 1 divided by x minus 2. Our common factor, our whole, will cancel out. So we're going to look at the limit as x approaches 2 of x plus 1. Plug in our 2 there, and we end up with 3. So it tells us that f prime of 2 is going to equal 3. So this is going to simplify our life a little bit so that we can find the value of a derivative at a specific point in time. So with that, we can go ahead and find the equation of a tangent line a little easier than we did yesterday. So we're going to find f prime of 1 because we know our x value is 1. So we're going to have x to the third minus our f of c. Plugging in 1, we get 1 again over x minus 1. X to the third minus 1. Factoring a perfect cube. Oh, your favorite. Hopefully, some of you recall how to factor a cubic. We can take the cube root of x to the third, which is x, cube root of negative 1, which is minus 1. To get the trinomial, we square the first term, so we get x squared. We multiply the two together and change the sign, so plus x, and we multiply the last one to itself, or square the last term. And that's going to give us x squared plus x plus 1 divided by the x minus 1. Oh, forgot my limit, didn't I? So limit as x goes to 1 as well is in there. So x minus 1 is going to cancel. So f prime of 1 is going to equal the limit as x approaches 1 of x squared plus x plus 1. Plugging in our 1, we get 1 plus 1 plus 1, which gives us 3. So that's our slope. We can also find our y value since we know the x value. So we can find f of 1. 1 to the third is 1. So we have the slope of 3, 3. We have the point of 1, 1. Now we can write the equation. Y minus 1 equals 3 times x minus 1. If you want to manipulate this, you can. Again, we can leave this as extended response. Multiple choice, you're probably going to see it as y equals 3x, multiply your 3 through, we get a negative 3, add your 1, so we get minus 2. So it would probably be in this form when we see it. You could also see it if we manipulate it. How about 3x minus y equals 2? Something like that. We could subtract the y off, add the 2 over. Again, any combination of this could be seen on a multiple choice question. In order to estimate the derivative numerically, so numerically just means that we're given a chart, we're given some numbers. We can estimate the instantaneous rate of change using the average rate of change. If you recall, when we talked about the definition of derivative, we took the secant line, or the average rate of change, that slope, and we made it get closer and closer and closer to the tangent line. And this is what is happening within a chart as well. So if we take a small region or a small set of numbers, then we can estimate what that instantaneous rate will probably look like. It's not going to be exact, it's going to be an estimate, as long as our points are fairly close or relatively close to each other. So how do I estimate f prime of 2? Well, if you notice here in our chart, we're given the x values and we're given the y values. We can estimate f prime of 2 by taking the values that are close to around 2. So 2 would fall in this region here between 1 and 3. If I take this information, so the x values of 1, 3, and the y values of 4, 7, that's going to give me a good approximation of what's probably happening around 2. Is it going to be exact? No, it could be completely wrong and completely out there. But generally speaking, again, we can estimate it. So f prime of 2, instead of being equal to, we're going to say it's going to be close to or approximately. Well, what is it approximately to? It's going to be approximately f of 3 minus f of 1 divided by 3 minus 1. And I'm going to put this notation in here. This is a very important notation for us in calculus, because these values, if we just put in 7 and 4, we don't necessarily know where 7 and 4 are coming from. They could be anywhere down in this chart if they repeat it. So if I maybe, instead of a 14, this was a 4 and this was a 7, we don't know which 4 or 7 we're talking about. But when I put f of 3, I know I'm talking about this box. F of 1, I'm talking about this box. So very important that we have this notation to show people and to tell people exactly what values we're pulling. So now that we know that, we can go ahead and find f of 3. F of 3 was 7. F of 1 is 4, divided by 3 minus 1. 7 minus 4 gives us 3, divided by 2. So f prime of 2 is approximately equal to 3 halves. Can we estimate f prime of 1? This becomes a little more complicated because we're given 1 here, but we can't estimate at a point given just a set of points. So what we have to do is, again, estimate it using things that are close to it. Well, what is close to 1? Well, here 0 is pretty close to 1, and 3 is fairly close to 1. 0's a little closer than 3, but we could actually use either set of these points. So again, we could use, or we could say that f prime of 1 is approximately f of 1 minus f of 0 divided by 1 minus 0. Or you could say f of 1 is approximately f of 3 minus f of 1 divided by 3 minus 1. Not that we have to do both. We're going to use one of them, and it doesn't matter which one you use. It's kind of arbitrary here at this point. This one's probably a little better because these points are a little more relatively closer than these 2 points down here. But again, 0 and 1 and 1 and 3, you're not looking at a major difference. You wouldn't, however, want to use 1 and 10. That's pretty far off, comparatively speaking. So what do we get here? Well, f of 1 gives us 4. F of 0 is 2 over 1 minus 0, or 2. F of 3, working this one down here, would be 7 minus 4 over 3 minus 1, or 3 halves. Not that it's always going to work out this way, but notice these 2 points or these two slopes, instantaneous rate change, are pretty close to each other. 3/2 and 2, you're not going to see a big difference if you were to graph those two slopes on a small interval, relatively speaking. Oh, got a clean sheet of paper. I don't know how that got in there. All right, the last thing I want to talk about is an example of a problem that you might see on an AP test. It's a good little question. Can we find the equation of the line that is tangent to the graph of f of x equals 2x minus 1 and parallel to the graph 3x plus 6y equals 5? So what do we know about these things? Well, I know parallel lines have the same slope. So I'm going to write that down, same slope. And tangent, I know tangent means if I want to find the equation of the tangent line, the slope, I got to find derivative. So I'm going to have to find f prime of x as well. All right, well, can we find the value or the slope of this point here? The equation, 3x plus 6y equals 5. So I'm going to go ahead and start there. And I'm going to subtract my 3x divided by 6. So y is going to equal negative 3/6 x. I know it's negative 1/2, but I'm going to go ahead and write it out there. Plus 5/6. So I know my slope is negative 1/2. If I want these two to be parallel, I know my slopes have to be the same as well. So if I find the slope here, if I find f prime of x, the way we're going to do that is taking the limit as h approaches 0 of f of x plus h, so x plus h squared minus 1. From that, I'm going to subtract the original function, x squared minus 1, and I'm going to divide by h. Multiplying this out, I get x squared plus 2xh plus h squared minus 1 minus x squared plus 1. That's all multiplied out, distributed out. So my x squareds will cancel, my negative 1 and positive 1 will cancel. So I'm left with the limit as h approaches 0 of 2xh plus h squared over h. I can go ahead and factor out my h, so I get 2x plus h. My h's will cancel. So I'm looking at the limit as h goes to 0 of 2x plus h. Well, that gives me 2x, and that's my f prime. So what I'm looking for is the slope of this function, which is going to be 2x at any given point, to equal negative 1/2. What x value gives that to me? So I can take my negative 1/2 and set it equal to 2x. Go ahead and divide my 2 over, so I get negative 1/4 equals x. So I know my x value is negative 1/4. Well, if I know my x value, I can find my y value. My y value is going to equal that negative 1/4 squared minus 1. Negative 1/4 squared is going to be 1/16 minus 1, which is negative 15/16. So I have my x value, I have my y value, and I have my slope. Because remember, my slope is going to be the same, negative 1/2. So I can write the equation. Y plus 15/16 is going to equal my slope, negative 1/2, times x plus 1/4. And that's going to be my equation of the line that's tangent to the graph of f of x and parallel to the graph of 3x plus 6y equals 5. Hopefully that gives you a good sense of how we can apply this and some things that we're going to ask you to do with it. Happy, happy, happy days!